Professor Chen, distinguished participant, ladies and gentlemen, good morning, salam sehat dan salam sejahtera untuk kita semua. It gives us great pleasure to welcome all of you to the guest lecture on renal physiology organized by the Department of Biology, Faculty of Mathematics and Natural Sciences, Universitas Negeri Malang. As all we know, that physiology is the study of how the human body works. It describes the chemistry and physics behind body function, from how molecules behave in cells to how systems of organs work together. It provides a thorough understanding of normal body function, enabling more effective treatment of abnormal or disease states. The underlying goal in studying physiology is to explain the fundamental mechanisms that operate in a living organisms and how they interact. Besides satisfying a natural curiosity about how animals and humans function, the study of physiology is of central importance in biology, medicine, and related health sciences. For that reason, today we are holding a guest lecture on physiology with a very interesting topic, the kit and two cats, renal sodium and potassium physiology. I would like to take this occasion to express my appreciation to the keynote speaker of today's guest lecture, Professor Dr. Cheng Ming from University of Malaya, Malaysia, from Faculty of Science. And thank you very much for sharing your experience and knowledge with the academic staff and our students. Finally, in anticipation of a fruitful and successful guest lecture program, in the name of Allah Subhanahu wa Ta'ala, the beneficent, the merciful, Bismillahirrahmanirrahim, I hereby officially open this program. Good luck, have a wonderful time, and nice talk. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh. Our thanks go to Professor Dr. Hadis Wono, MSE, for the welcome that has been given. Before hitting the main event, we will do a documentation session. Those on duty are welcome. Okay, for documentation session, slide 1. Okay, slide 2. And slide 3. Slide 4. Slide 5. Okay, thank you. Before heading, next is the delivery of material which will be guided by Mr. Hendra Susanto, PhD, as moderator. Moderator are welcome.
Okay, thank you very much, Ms. Rafika, as the Master of Ceremony today. Assalamualaikum warahmatullahi wabarakatuh. Good morning to everyone. Respectable the Dean, Faculty of Mathematics and Natural Sciences, Universitas Negeri Malang, Professor Dr. Hadisono, MSE. Respectable Chair Lady of Biology Department, Associate Professor Dr. Sri Rahayu Lestari, MSE. the honorable all lecturers of the biology department, and the honorable all participants of this today guest lecture. Ladies and gentlemen, I am Hendra Susanto as the moderator of today's guest lecture. I am very pleased to see you here and welcome all of you to this guest lecture. Today's guest lecture is about the kid and two cats. I think the title is very unique, right? Renal, sodium, and potassium physiology. Ladies and gentlemen, our speaker today is Professor Dr. Cheng Hui-Ming. He is one of the experts of physiology at University Malaya, Malaysia. Professor Cheng is one of the scholars of International Union of Physiological Society, or IUPS. He has received his bachelor degree in medical cells biology and biochemistry at University of Liverpool. Also, he was graduated from the same university in the immunology field in 1983 for his PhD program. Just a little bit know that Professor Chong also was joined for his diploma religious studies at Cambridge University at the same years. So, before the presentation begins, let me inform how the presentation will be going on. First, Professor Cheng will be invited to present the material for about 50 minutes. And after that, the next 10 minutes, there will be question and answer session, and followed by the conclusion by me, actually, especially as the moderator. So now allow me to welcome the speaker, Professor Dr. Cheng Hui-Ming, to deliver his valuable talk today. To Professor Cheng, the floor is yours.
Thank you, Dr. Hendra, for the invitation, and thank you, Professor Hadi, the Dean, for welcoming me to speak to your students and staff. I recognize some colleagues here. So because the audience is biology audience plus I think a mixed audience, and I decided to do a general topic on the kidney and the two main cations that it control. And so I tried to make this an interesting, broad title and call it the obviously the kidney, and how it is involved in the regulation of these two major cations. And I'm very happy that some of the students are also involved with me in this presentation because we use this fun title, The Kid and Two Cats. So you will see some students with their cats or their favorite cats in some of the PowerPoint. This is just to engage you. So more general is trying to give you the big picture, bigger, a broader perspective of how the kidneys are involved in regulating the sodium and the potassium. So the slide, obviously, how that affects other functions by regulating extracellular fluid sodium and extracellular fluid potassium. So I'm going to share my slides now. It's not so many slides, it's a lot of pictures, and I hope that my colleagues and students can use this as a reference. I normally leave my contact number in the first slide. So, and I also ask Dr. Hendra to freely share my PowerPoint slide to anyone who wants, so that you don't be in a hurry to copy the notes. Okay, so just sit back and let's enjoy some physiology together. Yeah. So let me try to share slide, and I hope it works because I just bought a new laptop. So let's see. Okay. So not yet. Wait, hold on. Let me see. Share screen. Okay. Can you see this?
Just wait a moment. Yeah. Yeah, we already see your PowerPoint, Professor.
Okay, so yeah, so this is a cover slide and my contact number. So feel free, colleagues and students, to follow up on this lecture, not only within our short 10 minutes question answer, but even after this, be happy to interact with all of you. This is one student, I didn't get the names. Dr. Hendra managed to ask students who have cats to send me some pictures. So this I thought is an appropriate picture. Is a kid, of course, a student with 2 cats. So the next slide, so I will talk first about potassium and spend more time on sodium. And basically because in terms of the kidney function, which relates to sodium, it is involved in not just the what we call the sodium concentration, but also something called the sodium balance. So there's more information there. So most of the topic will be on sodium, but we start off with potassium. So the next slide is a little bit unusual because here it shows a triangle. And this is one of the recent ways in which we try to summarize small pieces of information so that it gives the student or the teachers a kind of visual mental image of certain physiology information. And this is already published as a paper recently. And again, I'm happy to share this paper with anyone. So we combine the 2 words here, geometry, obviously is a triangle here, and physiology. So we call this phi geometry and organizing physiology. So what we're looking now is potassium concentration, the first part, which is K here at the apex. And then obviously ECF is the extracellular fluid potassium, and ICF would be the intracellular fluid potassium. And so the 2 words on the side of the triangle is just to highlight that the intracellular fluid potassium, which is always very high, is controlled by this universal ATPase, whereas the extracellular fluid potassium, which is always very low, about 4 to 5 millimole, that is controlled by, I think most of us know this, the hormone aldosterone. So in other words, that when we think about potassium physiology, there's always a very steep transmembrane potassium gradient, very high inside and very low outside. The high potassium inside is due to ATPase. The low potassium outside is due to this adrenal hormone called aldosterone. And that maintains the very steep gradient. And I'm going to very quickly summarize that this transmembrane potassium gradient is then exploited by many tissues in order to effect many different physiological functions. So just the same gradient maintained by ATPase and aldosterone is then exploited. We will come to that in a short while. So this is basically an introduction. And the next slide is just to show you the overall control of potassium in the body, and also will direct your focus to the kidney. Okay. So this is just another way of putting it. So right at the left is basically just to make the same point that most of the potassium is inside the cell, tissue stores. So I tell the students, don't memorize this number. This is just an average number. So students tend to memorize numbers. Yeah. So it's just to show you that most of the potassium is in the cell, and compared outside, this is in millimole, much less outside the cell. But it is important to establish this gradient. So the main point here is that if you look at the amount that enters the body, about 100 millimole per day, so you find that most of that right at the bottom here, the kidney, is that most of that is actually excreted from the body. And this is obviously because every day on a normal diet, we tend to add in excess potassium to the body. And so it's very important to control the low level by secreting and excreting the excess that you take in on any kind of diet. You always add in more potassium. And so that's why that in patients with renal problem, one of the main problem is obviously the accumulation of potassium in the body. You tend to get hyperkalemia. So it highlights the very important role in a normal person in secreting and excreting the excess potassium, even on a normal diet. And here again, just to put in the two keywords in blue, the one that maintains a very high potassium, and the one in green letters, the one that maintains the very low extracellular fluid potassium. Yeah. Okay. So the next slide is a recent way of trying to engage our students, and I think as teachers we trying to innovate and be creative. So one of my biomedical students, not a medical student, has she likes to draw, and now we have created two Japanese characters. The lady is called Miss Take. Sounds like Japanese, right? Miss Take. Of course, Miss Take sounds like the word mistake. So Miss Take is talking about misconception in physiology. And then the other person is a male called OIC. It's like OIC, you know, it's like it begins to understand. So this is one recent cartoon about potassium. So let's just say, so here, hi, Ms. Take, you are an A-star student. Tell me, does the sodium potassium ATPase control the extracellular potassium? And then Ms. Take says, oh, I see. No, rather is the high intracellular. It's important to know which side that is maintained by the ATPase. Okay, the extracellular obviously is controlled by aldosterone, as we just said. And so OIC asks, so what regulates then the extracellular potassium concentration? We all know the answer. But in this case, the lady said, I will tell you when you buy me lunch. Okay? So let's move on. So here is just to summarize, and again, we have this young man here, handsome young man with his favorite cat. So we use the word renal handling to explain how filtration, reabsorption, and secretion, these are the three main processes when we use the word renal handling. How does the kidney handle or process any solute? So for today's talk, we're thinking about potassium and then sodium. So the general relationship for renal handling of potassium, what is excreted on the extreme left is what is filtered minus what is reabsorbed plus, and this is the important point we made in the previous slide, that on a normal diet, you need to have always secretion of potassium in order to maintain normal potassium, low ECF concentration. So the secretion component under the control of the hormone aldosterone is very important for potassium physiology. Then at this stage, let me just put it together in the context. For sodium, you find that we don't talk anymore about secretion of sodium in order to control sodium concentration or sodium. Here for renal handling of sodium is only filtration and in the bold purple letters here, reabsorption. We'll come to this in a short while. So this is generally the big picture of how the kidney process or handle sodium and potassium, depending on the status, whether you are in a negative sodium balance or positive sodium balance, negative potassium balance, or positive potassium balance. Yeah. So the next slide is just an example of how the potassium concentration is rapidly sensed by the body, and then it either secretes more aldosterone from the adrenal gland or less aldosterone. So, so there you are, increased potassium intake. So as I said, you don't really need to have a scenario where you have increased potassium intake because any normal diet will add in excess potassium. So following a meal, potassium rises in your postprandial blood. And in fact, one of the other hormones which is important to maintain potassium is actually insulin, as some of us know. Insulin tends to increase the activity of the sodium potassium ATPase, and so the cellular uptake of potassium is also increased by insulin, besides its role in uptake of glucose. But here we're focusing on the hormone aldosterone. So very quickly it is sensed by the body, and you get increased secretion of aldosterone, and aldosterone then acts in the kidney. That's where the action is, to increase the secretion of potassium. And so you get the excess potassium excreted. So the more potassium you take, the more potassium will be excreted because more of the aldosterone will be released. So this slide, when I show this, I would like to ask students this question, because when we think about homeostatic control, there must be sensors that detects the change. Okay, so I always like to ask students without giving them the answer, and I'm going to do this again here in my talk. So I'll ask them, where do you think the potassium sensors are that detects the potassium and then sends a message to the cells that secrete the hormone aldosterone? So this is a way in which we can hopefully stimulate interest by what is known as cell-directed learning. Obviously, in the next lecture, then I will tell them the answer. But I pose this question here to all the audience, students and colleagues probably will know, where do you think are the location of the potassium sensors that detects fluctuation in potassium, and that causes the change in the aldosterone secretion. So the next slide is name of a restaurant near my home in Johor Bahru. So this is my hometown in Peninsula. But I saw the name of a restaurant, and it reminded me of the rapid control of potassium concentration by the kidney. So it's a very funny name. So it says here, kedai makanan dan minuman, very okay. Very okay restaurant. So the K here, when I took this picture many years ago, reminds me of the fact that so much potassium enters the body through a normal diet, but it's okay for our body because we have this rapid control by one of the major hormones, which is aldosterone. So in just a few words here. So the low potassium concentration is maintained by the kidney. Now, what is the significance of this in terms of the whole body physiology? So again, this young lady here with a cat looking on, yeah, the low potassium ECF concentration, which is maintained by the kidney, is essential to maintain the normal excitability of nerve and muscle. Yeah, I think we know this as a basic core physiology. So which means that the kidney, second sentence, by maintaining the low potassium concentration, is helping to preserve normal nerve and muscle function. So I tell the students that the kidney is not just an excretory organ. By maintaining just this one cation concentration, it is indirectly affecting normal nerve and muscle responsiveness because it maintains the low potassium concentration. So how does this happen? Because as we said, there's always a steep potassium gradient, transmembrane gradient, and that very steep potassium gradient is responsible for what is known as the resting membrane potential. So when you change the external potassium, you change the transmembrane gradient, you also change the resting membrane potential. And when you change the resting membrane potential, obviously you alter the excitability of the nerve and muscle. Yeah. So the next few slides is actually normally done in almost 45 minutes, just to highlight that the same gradient for potassium, and I give this as a separate lecture normally, the same potassium gradient is exploited in many different organs in order to produce that effect. So let me run through, and I hope this, for those who have done more of physiology, you may recall some of this. So the first one we just mentioned, that the transmembrane gradient is important for resting membrane potential, and that affects excitability. Now, the second one is that in the synaptic transmission, we always think mainly of sodium entering in and depolarizing the postsynaptic membrane. But one of the other ways in which you can have depolarization is if you have a decrease in the efflux of potassium from the inside to the outside. So in some synaptic transmission, the ligand neurotransmitter closes the potassium channel and reduces the efflux that normally happens down the potassium gradient. And so that also produces the same effect. So this is an example of a synaptic neurotransmission that involves the potassium gradient. Now, in the fact that your heart is beating as you listen to this lecture is obviously due to the sinoatrial node. You have calcium coming in, with sodium coming in to the sinoatrial node. But the other cation that contributes is that during the pacemaker potential, there is actually a decreased efflux of potassium down that same gradient. Okay, these are 3 examples. Let me give you another 3. So we mentioned glucose, how the pancreas senses the hyperglycemia after a meal and then releases insulin. Obviously, it's very fascinating and well established now. The first step is actually the uptake of glucose tends to produce ATP, and that ATP closes some of the potassium channel and depolarizes the pancreatic beta cell, and calcium then comes in and causes exocytosis of insulin. So again, an example of how the potassium gradient is being used. And just very briefly, in pulmonary physiology, the very unique response of the blood vessels in the lung to hypoxia is not vasodilation, is vasoconstriction, because this is part of maintaining what is known as the ventilation perfusion balance. So if you look at the detail of this hypoxic vasoconstriction in the pulmonary vessel, it also involves a reduced efflux of potassium, and then it depolarizes the cell. And then calcium comes in and causes contraction of the smooth muscle. And then the last one here in lung physiology is how does the carotid bodies or the, how does the carotid bodies or the aortic body sense hypoxia? Again, let me just say in this brief time that if you look at the mechanism, it is also involving a decrease in the efflux of the potassium ion. So the same transmembrane potassium gradient, and that is possible because inside always high because of potassium ATPase, outside always low because of aldosterone, is then exploited by many tissues to effect function. Yeah. So the next slide is just a summary of more examples, and I'm just going to leave it without saying so much because of time factor. This is part of the talk. So these are, I just put it in the same letters, 9P for potassium physiology, and how in all these examples, and the first few we mentioned, it involves a decreased efflux of the potassium down its potassium gradient. And just to quickly say a few more, the fact that you can hear this lecture is because of the hair cells in your inner ear. And the mechanism there is very interesting because the fluid that surrounds your hair cells actually has more potassium than inside the cell. And so the entry of potassium down this mechanically gated potassium channel is the one that triggers the perception of sound and also the perception of balance in your inner ear. And this in our Asian enjoyment of sweet and sour food, the sour sensation is also involving potassium physiology. Yeah. Okay. I should move on now to spend more time on talking about the sodium physiology. So the same kind of diagram, the geometry of sodium physiology. So here again, now we know that the top part, we're talking about sodium concentration. So again, the extracellular fluid sodium, now for sodium is the reverse. We all know this. The transmembrane gradient for sodium is in the opposite direction. In all living cells, this is a very interesting phenomenon. The gradient for potassium is inside out, and the gradient for sodium is outward in. So the high extracellular fluid sodium is maintained by ADH. Okay, ADH, antidiuretic hormone. We're talking about concentration. This is vasopressin, the other name, and the low intracellular fluid sodium is maintained low by ATPase. We know that this ATPase, the full name is sodium potassium ATPase. It keeps the potassium low, it keeps the potassium high, and it keeps the sodium low in the cell. But outside the cell is different hormone. So in this case now, it is actually ADH. This may surprise some of you who are listening. You may think about sodium and that this should be aldosterone. Let me explain, hopefully, why it is actually ADH and not aldosterone. Okay, because here we're talking about sodium concentration. So, so the next diagram is also a kind of physiometry. I hope. So here this is coffee 3-in-1. Let me explain why there's coffee 3-in-1. So basically, these three parameters here: control of osmolarity, or what we call osmoregulation, control of water balance. We're interested in homeostasis, control of water balance, and then in the box here, this represents control of sodium concentration. So all these three functions actually means the same thing in physiology. They are synonymous: osmoregulation, control of water balance, and control of sodium concentration. They are all functionally part of the same mechanism. That's why we put them all together in this physiometric diagram, and with the coffee 3-in-1 here. So let's just give an example here. If you take in a lot of water, you are in positive water balance. So immediately what will change is your osmolarity, obviously. Your body fluid becomes hypoosmotic. But at the same time, because sodium concentration is the main determinant of osmolarity, you are also transiently hyponatremic. So when you homeostatically excrete the excess water, you are basically osmoregulating to bring the osmolarity back to normal. You are also controlling the sodium concentration by bringing the hyponatremia back to eunatremia, normal. So they're actually part of the same. And I think everybody knows that osmoregulation involves ADH, right? So in the last slide, we have this sodium concentration, because sodium concentration here is linked to osmoregulation, is linked to water balance. And since ADH is involved in osmoregulation, it must therefore be involved in the control of sodium concentration. So we're not talking about total body sodium. That is under aldosterone control. This is sodium concentration. So let me elaborate by the next slide. So since the sodium concentration in the ECF is the main determinant of ECF osmolarity, then we, for those of us who know that the osmoreceptors that are found in the hypothalamus obviously detect changes in osmolarity. But if you think about this triangle, if they all mean the same thing, it means that the osmoreceptors are functionally detecting changes in sodium concentration. Because like when you drink a lot of water, you are in positive water balance, your osmolarity goes down. It also means your sodium concentration goes down. So when the osmoreceptors detect hypoosmolarity, it is also detecting hyponatremia. It's functionally the same thing. Okay. So let's move on to a cartoon here. So this is just one of the few cartoons, one of my favorite cartoons, where there's some mention about sodium physiology. Now, I just leave this to you for enjoyment and whether you think the physiology here is correct or not. So I leave it to you, okay? Now, let's now distinguish between the two important aspects, which is very easily confused, and that is sodium concentration control, which is under ADH, and total body sodium control or sodium balance, which is under aldosterone. And one of the best examples to try to point this out is to give the example of a normal event, and that is during exercise. Okay, so next slide is to show you what. Now, the picture starts off by saying severe sweating. I don't think you need to sweat severely to produce this kind of picture. Just you can cancel out the word sweating. Severe. The sweating, obviously, sweat is a hypotonic fluid. You lose fluid, you also lose some salt. Okay, so on this right side is basically osmoregulation. So in this case, you've lost water. You are in negative water balance. You've lost water from the body. And so, so in terms of osmolarity, you are now your body fluid is now hypertonic, obviously. Now, in terms of sodium concentration, remember that triangle? Your body fluid is obviously hypernatremic. Right? It's the same thing, the three things. So when you, in this case, when the hypothalamic osmoreceptors detect the hyperosmolarity or the hypernatremia, then you release more vasopressin, and we know that vasopressin acts in the kidney to conserve more water, reabsorb more water. Less water is excreted. Your urine is more concentrated and more hypertonic. So this part on the right here is osmoregulation. It involves ADH that normalize the water balance from negative to normal. It normalizes osmolarity from hyperosmotic to a normal osmolarity. It also normalizes the sodium concentration from hypernatremia to normal sodium concentration. Now, on the left side is what we're going to talk about the next few slides. At the same time, when you're losing sweat, you always lose sodium because any body fluid will contain sodium. Anytime you lose body fluid, whether it's blood donation, whether it's, in this case of the exercise, you are in negative sodium balance. Okay, so now if you think about it, see, you are hypernatremic if you look at the right side, but you are also in negative sodium balance. So the two things actually can happen. You can be hypernatremic, but because you've lost sodium, you are in negative sodium balance. You are hypernatremic because you have lost more water relative to the sodium. That's why it's more concentrated. Now, in the case of sodium balance, in order to recover this sodium balance, what will always happen in the kidney, as you see here at the bottom here, is the kidney will always respond by excreting less sodium. It's trying to conserve sodium in order to restore the sodium balance. So which means I tell the student that every time you go and to the toilet to wee or to pee, it is not just an excretion. You are actually performing homeostatic work. Yeah, so because the amount of sodium that you excrete in the urine is in response to changes in sodium balance. So in this case, negative sodium balance, so you will need to excrete less sodium in order to recover more of the sodium, and then sodium will then help to the total volume, body sodium, or what we call sodium balance, will then help to restore eventually the ECF and the plasma volume. And the two things that happens now, so here you have now aldosterone, okay? So aldosterone is on the left side, not on the right side. Okay, aldosterone is involved in sodium balance, okay? Not in sodium concentration control, yeah. So this takes a little while for students and also for some of my junior colleagues to try to appreciate so that they are able to communicate it better to the students. Now the GFR here is mentioned as being reduced. Now this means that in the compensation mechanism, the whole mechanism is more complex than this, obviously. When you reduce the GFR temporarily in order to restore sodium balance, basically what you're doing is that since sodium is filtered, you are filtering less sodium. When you filter less sodium, remember the picture of the zebra I showed you? The renal handling of sodium is E equal to F minus R. So if you want to reduce E, right at the bottom here, you will always reduce F, you will always increase R, which is increasing the plasma aldosterone. Okay? So basically this is the next slide, just to remind you how sodium balance is compensated by the kidney. You always increase R, you always reduce F if you are in negative sodium balance. So this is the next slide, changes in ECF volume. And ECF volume is determined by total body sodium, is always compensated by changes in urinary sodium excretion. So E excreted is F minus R. So in the case of our example in the last slide, because you are in negative sodium balance, you have lost sodium in your sweat, you want to reduce E, so obviously you reduce F and you increase R. So and within this big picture, then you can fill in the details for the student. So I just mentioned here under the red part, the reabsorption of sodium is obviously under the hormonal, which is the renin, angiotensin, aldosterone system, RAAS. And also under this interesting branch of the sympathetic nerve, renal sympathetic nerve. So this is interesting, right? That the nerve is involved in the sodium cation control. Yeah, so so I just put this here. Now, so the next slide is a bit more complex, and because some students may not have done renal physiology, but I just leave this, as I said, don't be too anxious to copy notes. So I'm just going to detail slightly about this renin, angiotensin, aldosterone system. So whenever, just to make the point, whenever you are in negative sodium balance, you always increase renin, because the purpose of this system is to restore sodium. Okay, whenever you are in negative sodium balance, you will always stimulate the release of this hormone, renin, from the kidney, and then that will lead to angiotensin 1, 2, and aldosterone. And aldosterone, as we know, is the one that finally will reabsorb more sodium. Okay, so the next slide I leave to you as a reference is that so this mechanism is very fascinating. There are actually 3 ways in which renin will be increased whenever you are in negative sodium balance. Okay, so so normally before a very complicated slide, I warn the student. Normally when you tell the student it's going to be complicated, fasten your seatbelt so they are prepared. So fasten your seatbelt. So this is the slide about 3 ways in which renin is stimulated when you are in negative sodium balance. So here you are. Okay, so so it's always good to look at the top and the bottom first. So at the top is I can't see this on my slide, but so we're talking about low volume. Whenever you've lost body fluid, you are in negative sodium balance. And then before you look what is in the middle, look what happens at the bottom. You decrease sodium excretion. You want to conserve sodium, right? And because you want to conserve sodium, you always you go upwards now. We go back to front. You always increase aldosterone in order to reduce sodium excretion. Now, in order to increase aldosterone, obviously this comes from renin, right? Yeah. So you put it this way: every time you lose body fluid and you enter into negative sodium balance, you always will increase renin. And here it just shows you the 3 pathways for renin secretion. So I'm just going to say this briefly because this involves a more elaborate explanation. One is a structure, very interesting structure. I just call it MACD, not McDonald. It's the macula densa, where there's a signal during negative sodium balance that will stimulate renin. The macula densa is just next to the cell that has this granules that will secrete renin. And then the second pathway is actually, as I mentioned, the renal sympathetic nerves are involved in sodium control. And one of the ways is that the cells that secrete renin are innervated by renal sympathetic nerves. So this is, the renal sympathetic nerves are always activated because of the hypovolemia. You activate your barrel reflex, and that obviously increases sympathetic activity to many parts of the body, which includes the kidney. So the renal sympathetic nerve also stimulates renin. And then the third pathway, so all these 3 pathways occurs at the same time. The macula densa, the renal sympathetic nerve, and the third one is the RPP is renal perfusion pressure. Basically, this is just the renal arterial pressure. So when your blood volume is decreased, your arterial pressure is decreased. Obviously, the pressure sensed by the kidney will also be decreased. And this one has a direct effect because it involves some mechanosensors at the efferent arteriole. This is where the renin is released. So direct sensing, and when it senses a drop in the pressure, it will release renin. Because what it is assuming is that the decrease in pressure must be because the volume has dropped and you are in negative sodium balance. That's how the design of the the detection system. Okay, so this is a useful big picture in order that students can use and the teachers can also use to describe further about the detailed mechanism. Okay. So yeah, so the point we just made is that aldosterone is involved in negative sodium balance and not in hyponatremia. Okay, let me say this again. Aldosterone is increased in negative sodium balance, but not in response to hyponatremia. Because when you say natremia is sodium concentration. So this is perhaps an important point to just think through. And it always surprises a student that the sodium concentration is not controlled by aldosterone, but by ADH. Remember okay. So I just put up this picture that the element of surprise always challenges and engages a student to think, if they like to think. Okay. So this is so the element of surprise always challenges and engages. So I think we know who this other person is. Yeah. So this is the statement here. Ecf sodium concentration is not regulated by aldosterone. So if you want to make this sentence correct, then the first part should be sodium balance is regulated by aldosterone. Okay. So, or if you want to put this sentence correct, Ecf sodium concentration is regulated by ADH. Okay. So, so this is basically one of the ways we in the course of our teaching, we try to uncover or unmask. We use the COVID language, unmask misconception for our students. I managed to take a picture of this. This is unmasking misconception, because to show the students that the more correct picture. Okay? So let's go back to this picture. So this is again, there's a new cat here. So this is just because it's an important diagram, I just put it up again. Now just a few more slides and then, yeah, okay. So I mentioned in passing, and is that the volume of ECF, and which also means the volume of blood, obviously is related. Blood volume is part of ECF, is linked to the sodium balance. So what this means is that the kidney, by regulating sodium balance, is affecting the blood volume. And so that is why we say that the kidney is also involved in blood pressure regulation. Because if the kidney can maintain normal sodium balance, it is helping to maintain normal ECF volume and blood volume. And blood volume obviously affects blood pressure. So we talk actually of not just the heart in maintaining blood pressure, but also the kidney. So it's important to tell our students that there is this integrated cardio-renal mechanism for maintaining blood volume and blood pressure. And the kidney is obviously involved in the blood volume control through maintaining sodium balance. Okay. So just to remind the audience that renal control of blood volume is through maintaining sodium balance, and this involves what we just said, renin-angiotensin system. Every time you lose volume, you go into negative sodium balance, you always trigger through the 3 pathways renin secretion. Okay, and I have just mentioned that one of the 3 pathways is the renal sympathetic nerves that activates renin secretion. Now, in teaching renal physiology, it is convoluted, and so we try to help students to see that there's always a pattern as the filtrate moves down the very long journey, the nephron journey. So this is just to illustrate that for example, for sodium and potassium that we are looking at, there's actually a pattern in which we find the first part, the loop of Henle, and then the later part actually controls solute. So we try to help students to see sort of a kind of pattern. So this is, yeah, so excuse the language. This is the obviously periodic table. This is obviously talking about renal physiology. This is Mendeleev, the one who discovered the actual periodic table, the chemistry. So if we look at these 3 substances, water, sodium, and potassium, the first part different mechanism, but basically it's reabsorption. The second part is also absorption, obviously at different parts. Here is descending for water, because the ascending is always impermeable to water. Here, if those of you who know your loop of Henle physiology, it actually involves a shared transporter. We call this the sodium potassium 2-chloride transporter. It's a triple co-transporter that reabsorbs both sodium and potassium. At the collecting duct, water obviously is reabsorbed under ADH. Now, the same hormone aldosterone actually is involved in this dual task of reabsorbing sodium and secreting potassium. So it's very unusual. One hormone is a multitasker. It has two different action and acts on the same cell. It increases sodium reabsorption and also increases potassium secretion. There must be a reason for that. Why use one hormone to have these two important effects to maintain potassium balance and sodium balance? And I think just to give a bit more detail, so this is the collecting duct. The name of the cell is called principal cell. It's like the same spelling as headmaster of a school, principal cell. So this is the lumen side, and this is obviously the interstitial side, and the red one is the blood vessel. So when we think of secretion, it is from the blood side to the lumen. If we think of reabsorption, is from the lumen into the peritubular capillary. So let me just, okay. So the same cell, principal cell, is acted on by aldosterone. And obviously the sodium potassium ATPase on the basolateral side of the epithelial cell is stimulated by aldosterone. So as we said, this molecule always maintains potassium high in the cell and always maintains sodium low in the cell, ATPase. So same for any cell in the body, including this principal cell. ATPase has this universal, ubiquitous, very important function. Keep potassium high, keep sodium low. Now, for secretion, obviously, for potassium is this direction into the tubular fluid, and then it can be excreted. Okay. For sodium, is obviously recovering sodium from outside through the luminal membrane, and then once it enters, it is just pumped out. Okay. So the secretion, trans-epithelial cell secretion, and the trans-epithelial cell reabsorption of these two solutes is obviously an active process, because as long as one of the steps is active, which is obviously the ATPase, the whole process is considered as active. Although this step here, using the channel, is separately passive, because it just involves a gradient, as you can see, and the gradient here. Okay? But the second step to complete either the secretion or the reabsorption is active. So the overall transepithelial transport is considered as active sodium reabsorption and active potassium secretion, both by aldosterone. So in my final few slides, I just want to highlight, remember right at the beginning, I said that the kidney, by maintaining the low potassium concentration, actually fulfills indirectly a function to maintain excitability of the nerve and skeletal muscle. And so in the same way, the kidney, by maintaining a high sodium concentration, is also helping to maintain that gradient. Remember, we talked about this sodium gradient. So the same kind of concept. So the sodium transmembrane gradient, remember the triangle, we said sodium is always high outside and it's always low inside. It's low inside because of ATPase. It's high outside is because of ADH. Sodium concentration is about 140 millimole outside, and that is controlled by ADH. Part of that triangle where we have osmoregulation, control of water balance. Now, so this, and then the second and third point is just to remind us to distinguish between sodium concentration control and sodium balance. Sodium concentration control, ADH, sodium balance regulation, aldosterone. So now I'm going to just summarize that. So now when we look at sodium, that same sodium gradient is now being exploited in many different organ events. So the gradient is maintained by ATPase and ADH. ADH keeps the sodium concentration about 140 millimole high, and ATPase keeps the sodium concentration low. And because you always have that gradient, then that gradient is now exploited in many different events. Okay, so let me just summarize by using another diagram. So sodium transmembrane gradient, I've used this transmitted by sodium. Here it reminds you that your action potential, a lot of your action potential is transmitted by sodium because of depolarization. So, and this is because you already have that gradient, okay? And then the second major pattern that you see is that a lot of solutes, I think we know this, are transported together with sodium using the potential energy that you already have in the sodium gradient. And this can be either, as this diagram shows you, with you have either sym-port, co-transport, or antiport. So some solutes are carried into the cell by sodium or out of the cell by sodium. For example, let me give you, glucose is obviously transported into the cell by sodium. And then for proton, proton is transported out of the cell by exchange mechanism. So transported by sodium includes both co-transport and counter-transport. So we actually call this, we use the word secondary active transport coupled to the sodium gradient. Okay, and then the last point, and so this involves many different solutes. Just give one more example: the transport of iodide into the thyroid gland in order to form your what do you call that, thyroid hormone, uses a sodium iodide transporter. And then the last point is that in many situations, as sodium is being transported together with other solute, it generates a local osmotic gradient, and then water follows. So everything is linked. Okay, so so the next slide is just to list down some examples. I'll leave this for your reference. So we can, I use this slogan: no sodium gradient, no life. So that same gradient, which is maintained by ADH acting on the kidney, and ATPase is involved in axial potential, sodium influx, is involved in cardiac physiology, where you have sodium-calcium exchanger, is involved obviously in absorption of many solutes, amino acids, glucose in the intestine, and as I just said, water follows. So indirectly, the absorption of sodium together with other solute generates the osmotic gradient. And this is the one important in pH control, because hydrogen ion is secreted using the sodium gradient that powers the transport. And endocrine, I just mentioned, the sodium iodide transporter. Yeah, so many other examples that students can think of as they go through the whole of the physiology curriculum. So just in some words, and this is my second last slide. So the sodium concentration is high at this, and the potassium concentration is low. These are the two concentrations maintained by the kidney. So the potassium concentration outside the cell is actually at least 30 times less. Okay. Now the sensors in the body are set to detect fluctuations of both sodium and potassium concentration. The feedback and final effector organ in homeostatic regulation of these two cation concentration is the kidney. Okay. So for sodium concentration, we are already given you the answer. The sodium concentration detectors are actually your hypothalamic osmoreceptors, because by detecting osmolarity, you are actually detecting sodium concentration. The other question is, where are the potassium concentration sensors? I haven't answered you, so I'm going to leave this question unanswered. But the sensors for the ECM are not located in the kidney. Sodium is in the hypothalamus. So where are the potassium sensors? So we leave this question open to the students to think through. Yeah, so I think that's okay. So thinking through physiology is one of my emphasis as I go interact with my students to challenge them because physiology is a dynamic science. So you really need to allow time for the students to process it in their own minds. Yeah. Whereas learning other subjects, anatomy, maybe it requires a bit more recall and memory work. Yeah. So, and just one last slide to acknowledge those of Hendra students who kindly sent me all their cat pictures. We don't have time to put into all the slides. So here are some of the students. I hope to hear from you. You can let me know your name and the name of your cats. So I hope that this talk on the kidney and the role of two cat ions, the kid and two cats, has been helpful to you. Yeah. So here you are, all the beautiful cats. So I think that is my last slide. So thank you for listening. Yeah, thank you. Right, I'll pass the time back to Dr. Hendra.
Okay, thank you very much for the interesting and valuable talk, Professor Cheng. And I think to all the participants now, we are going to the room session, I think, right? We have to go to the question and answer session. I think one of our colleagues here already raised hand. Dr. Dwi already waiting for you, but later we can know what is her question. So I think we will try to separate the session, maybe only one, right? Because we only have 10 minutes, right, Professor? 10-minute question and answer session. So the first question, maybe I will ask Dr. Dwi to deliver his question, her question to you. Okay, Dr. Dwi, time is yours.
Thank you so much, Mahendra. Professor Cheng.
Hi, hello.
I'm not a physiology person. I'm not a physiology scientist. I'm working in the development regulation, but it is a very interesting since last 2 months I experienced heart issues. My heart, this part, the cardiac issues, not the heartbroken. And when Dr. Hendra saying about a kid and 2 cats, I was wondering really what it is. But then in your almost last slides, it was answered. It is about cations, right? Cats, yeah. And the kidney. Yeah. But you talk also, but the cats also doing something for other organs, right? And then it was also almost a question about the balance regulations about these cats, potassium, sodium, and also calcium. But the major concern is about calcium, potassium and sodium, which in cell biology always we talk these 2 cats in active transport.
Right.
And is it matter that quite jumping in other things, the circadian clock changing and the psychological states, because you talk also about the hypothalamus. So I'm thinking about the neural, endocrinal neural connection, working on this phenomena about the cats.
Yeah.
So it is matter that the circadian clock change and the physiological state, current physiological state in do the balance or imbalance of these 2 cats.
Yeah, so the definitely for the blood pressure, which is indirectly linked to blood volume, there is circadian changes during the day. But of course, those changes will probably not be directly involving blood volume, because changes in blood volume will take time. So for the diurnal changes, it is most likely neural reason, perhaps, yeah. or maybe even endocrine. Yeah. So for the small changes that you see during a day is most likely due to other factors rather than concentration of the sodium. Yeah. So I think it would involve more rapid changes that produces the fluctuation that you see during the day. Yeah.
So it is not always about the diet or our intake of these two.
Yeah, because the diurnal rhythm is centrally controlled, so it cannot be due to your meal times. Yeah.
I see. Thank you so much.
Okay.
Dr. Cheng, yeah, it is very interesting, of course.
Thank you.
Okay, thank you very much, Ms. Dwi, and
thank you, Pak Hendra.
Okay, you're welcome. For the next question, I think it seems like very unique question in our chat box here, Professor. This is from our student actually, Pak Gede Sudirgayasa. He's from Bali. I think you know from his name. In case some people still believe that drinking their urine in the morning will be useful as a cure for certain diseases, does that make sense? What is your opinion, Professor? That's his question.
Yeah, I have heard about that, but I don't know the logic behind it, because in terms of homeostasis, which is the maintenance of the constancy of the internal environment of your body. So the compensation is obviously one of the kidney is one of the main compensation. So what is excreted in the urine is actually it's not just is the result of the homeostasis. You want to keep the internal constant. That's why you excrete either more or less sodium. That's the physiology concept. So by drinking what has been removed back into your body, I don't know whether that would fit into homeostatic, because you already maintain your body constancy by excreting more or less in the urine, whether it's sodium or potassium. So if you add it back,
a little bit confused, right?
Yeah, I mean, thinking physiologically, it would not make homeostatic sense. Yeah.
Okay, which means that if we use our waste material and return back to our body, we are not sure how the mechanism they can induce our physiological process, right? Seems like that. Okay, thank you very much. Okay, we are waiting for the next question. Here we have another question from Mr. Azril Febran. Okay. Oh, I'm not sure what is the question actually. Professor Cheng, I am sorry if I heard wrong based on the material that you described. How about the testing process? How about the testing process on the cat? How far has it gone? I'm not sure what is the meaning of this question actually. So can you ask the question directly to Professor Cheng, Mr. Azril Febrian? Can you hear me? Hello?
Hello.
Okay, you can you can ask the question directly to
please.
Professor Cheng. Yeah, please make it more clear. Okay.
Sorry if I heard wrong based on the material that you described. How was the testing process on the cats? This is Kalium and the cats. How far has it gone?
Oh, the cat is a mammal, so most of the physiology here would apply to cats. But the cat here is just for to engage the audience. So we're not really focusing on the cat physiology. But if you're asking about whether the sodium and potassium physiology is the same in the cat, I would assume it's the same, because they are also mammals.
Mammal, right? So this clear, right, Mr. Azril? Professor Cheng already clearly explained to us that it's just the symbol. We use cat because we want to describe about cations, not the real cat. Yeah.
Yeah.
That's only the symbol. So that's why I try to ask my students to send me their photo with their own cat and send to Professor Cheng. Just a symbol, not really about the cat physiology. It's about the cation.
Oh, I'm sorry. I'm sorry.
Sodium
I was
and
wrong about that.
potassium physiology in the kidney.
Sodium and potassium cat ions.
Yeah,
cat
cation.
ions.
Potassium and
Yeah. Because both of the ion is I mean like the charge is positive. We call cation, right? Cation, not cat. Okay, it's okay. Okay, I think we are waiting for the last question, Professor Cheng. Maybe somebody want to ask. Maybe Dr. Hardian want to ask something to Professor Cheng. I think he's so focused on his exhibiting, so we cannot ask him to deliver his question. Okay. Anybody want to ask question to Professor Cheng for the last question in this session? Okay, we are waiting for someone. Is there anybody want to raise your hand to ask question to Professor Cheng directly? Hello, anybody? Oh, Mrs. Dwi again. Okay, just continue your question. Yeah.
Hello.
Just come back, Professor. Just come back. Okay, okay, go ahead.
Thank you. Still concerned about these two cats, but not with the kid, but with the heart. And since you talk also about the role of these cations in diastole pressure, and in such a situation where when the circadian, again, so about circadian clocks is interrupted change, is it possible then that I don't know if there any relation with the aldosterone and ADH involvement in maintaining the balance of these two cats, which then affect in, for example, high in diastole or low in diastole pressure in heart cells.
Yeah, I'm not a cardiologist, so I wouldn't be able to. Yeah, the diastolic pressure is one of the key factor that affects diastolic pressure is actually the vascular responsiveness, the state of the total peripheral resistance. So so I wouldn't imagine there will be a direct effect of the sodium or the potassium concentration. Maybe the potassium, because the potassium concentration can affect, as I said, in passing, the excitability of the nerve and muscle.
Of the nerve muscle.
And that also includes smooth muscle. So maybe more for potassium. I think there may be some relationship, but I'm not aware of whether it's a well-established relationship between changes in potassium concentration and vascular responsiveness.
Vascular constraint. I see.
In terms of the diastolic pressure.
Well, in the daily life, we most talk about sodium in our diet, salt and salt for this food and for this something we cook. But I really am not familiar with the source of potassium in this sense. So how, in simple way, how can we control our potassium sodium balance in daily life?
Yeah,
thank you.
For the sodium balance, as long as your sodium balance regulation is effective, it is controlled by the kidney mainly. For potassium is also the key organ is also the kidney. As I said that in patients with renal problem, one of the complication is accumulation of potassium because they cannot secrete and excrete the excess potassium. So so kidney function is obviously important to maintain both the sodium and the potassium concentration.
So then what to say? The most important is to take care of the kidney. The kid with the kid for Azriel, the kid to maintain 2 cats.
That's right.
We take enough water
in
drink. Of course, it is normal water, right? Not the mineral water or something else. Thank you. So I have a better view than about this kitten to cats, and also how these 2 cations affect our daily life and how we should control it.
Right.
In a simple way, in the way I understand.
That's fine.
So, well, thank you so much.
Thank you.
It is meaningful so much.
You're welcome, Mrs. Dwi. So, like I said before that we don't have enough time to extend our discussion session. I think Prof. Cheng also has another schedule after this session. So before I close this session, please allow me to make a brief conclusion that both of these cats play a vital role in the body fluid homeostasis and also controlled by the kidney. And as we know that from the previous slide in the today material, that kidney is very, very vital for body. So because sometimes somebody a little bit not aware about how to maintain their kidney, they don't care about how to drink regularly with the enough volume or something like that. So I think we are finally come to the end of this session, and I would like to thank to Professor Cheng for the informative, valuable, interesting topic about 2 cats and the kids that make all my students a little bit confused, and they have a lot of curiosity about what is actually the cat and
me too actually
and the kids, because like all of them think, oh, this is about both, it's about baby, it's about the cat, but not actually it is related to the cat and the kidney. So finally, please give the big applause for our speaker today, Professor Dr. Cheng Heming from University Malaya. Okay, give applause to him.
Thank you. Thank you so much.
Thank you very much. I think we are already at the end of the session. I will return back the session, and I will close the session to I will back to the Master of Ceremony. Okay.
Thank you, Hendra.
Thank you very much, Professor.
Okay, thank you to Mr. Hendra, PhD, as moderator, and thank you also to Professor Dr. Cheng H. Min, who is willing to deliver today's material. Hopefully, the material presented today is useful for all of us in the future. Alhamdulillah, we have arrived at the end of the guest lecture event. Thank you very much to the presenter, moderator, invitees, and participants who have listened to the event from beginning to end. I am Rafika as the Master of Ceremony at the guest lecture event and representing the committee in chairs of apologizing for our mistakes and shortcomings in guiding this event, and thank you for your attention. Keep it up and stay safe. Wassalamualaikum warahmatullahi wabarakatuh.
Okay.
Thank you so much, Professor.
Thank
you so much, Professor.
Thank you.
Yeah, I'm sorry, I'm in the middle of exam, so I cannot hear clearly, and also I cannot ask you. Actually, I have a weird question for you, Professor.
You can ask it now.
Yeah.
Maybe next time. Maybe next time. We
Yeah.
can discuss
Yes,
about
in
it.
the middle of exam. Yeah.
Yeah.
Sorry. Yeah.
Okay.
Yeah. Thank you,
Okay, thank you
Professor.
very
Yeah.
much,
Thank you.
Thank
Professor.
you.
Thank
Bye-bye.
Thank you very
you.
much,
Thank you
Brother
so much,
Cheng.
brother. Yeah. Thank you. Yeah.
Thank you
Bye
very
bye.
much.
Thank you so
Bye.
much.
See you next time.
Yeah. Yeah. For all. Thank you. Yeah. Yeah. Always
Thank you,
in help.
Professor.
Yeah.
Thank you.
Yeah. Thank you, Dr. Hendra. Thank you, Dr.
Thank you very much,
Titin. Thank
Dr.
you. Yeah.
Thank
Thank
you,
you.
Dr. Hendra, Dr.
Oh,
Hadia.
thank you very much. Thank you very
Yeah.
much
Dr. Titin.
for
Thank
joining
you.
us.
Yeah. Dr. Agus. Yeah. Thank you.
I think